Hello and welcome to the next lesson. Today we're going to be studying binary and denary number systems and how to convert between them. So if we have a look, we're going to be studying most of this section here. So how to convert positive denary numbers, how to add two binary integers together, and we're going to be studying binary shifts, and we'll look at all the good hexadecimal stuff in a future lesson. Otherwise, this would take about an hour.
1 hour later.
As we should remember from previous lessons, computers store and process data using only binary numbers. So it doesn't matter if it's text or images or sound or anything else, we can only store it and process it in our computer systems using ones and zeros. So a binary number is a 0 or a 1, and this is known as a bit, which is short for binary digit. We now need to understand the concept of binary numbers in more detail. In day-to-day life, we use a number system called denary, or decimal, which is based on multiples of 10. Let's take the denary number 107 and see how it is made up. So we can see 107 is made up of 7 units, no tens, and 100. So we have 100 plus no tens plus 7 units, and that would collectively give us this 107. Notice, every time we move a column to the left, we're going up by a multiple of 10. So there are 10 units in a 10. There are 10 tens in 100. If we were to continue this, obviously the next column would be thousands, and there are 10 groups of 100 in 1,000. Binary is a number system based on 2 rather than 10, because binary only has 2 values, as we've discussed, 0 and 1. This time, every time we move from right to left, we go up in value by a multiple of 2. So we start with 1 as the smallest value. If we jump one column over, it doubles in size. We have 2's. And then if we jump again, we get to the 4's again, going up by a multiple of 2. Then we have 8, then we have 16, 32, 64, and then 128. And that's if we're looking at an 8-bit number. Obviously, we could continue that. The next one would be 256, then 512, then 1024, and so on and so forth. So let's have a look at binary to denary conversion. What is the 8-bit binary number 100111101 in denary? Well, we write down our table with the values from 128 to 1, and then we just fill in all the ones and zeros in the right place. Obviously making sure we do it in the correct order. So we've got our 100111101 in here. And then all we have to do is add together all the values that have a 1 in the column. So if you look at that, what values do we have? Well, yes, we have 128. There are no 64s in this. There are no 32s. Yep, we've got a 16. We've got an 8. We've got a 4. No 2's, but we have a 1. So let's add them together. That's 128 plus 16 plus 8 plus 4 plus 1, and that gives us a grand total of 157. So 1001101 is, in decimal, 157. A little bit of vocabulary note. We've got the MSB, or most significant bit, and that is the value furthest to the left. That has the highest value. And we have the LSB, or least significant bit, and that is the value furthest to the right, and that is the smallest value. So sometimes you will see references to MSB and LSB, and that just means most significant bit and least significant bit. Using 8 bits, the largest possible value we can get is 255. So if we get 8 ones, 11111111, I think I got that right. It is a lot of ones. We can see that gives us 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1. And if we add all those together, that gives us 255. So therefore, 8 bits gives us a range of between 0, if we just had 8 zeros, and 255, which is 8 ones. If you take a look at this example, the leftmost zeros have no value. So these zeros here are just placeholders to make up the full 8 bits. The numbers that have meaning, that have value, are the ones over on this side here, the values ones. So these leading zeros are not really important. So therefore, 0, 0, 0, 1, 1, 1, 1, 1, 1, and 1, 1, 1, 1, 1 are the same. Okay, so if you see either of these in the exam, they have the same total value, yeah? Because these zeros technically aren't holding any value, they're just placeholders. Let's look at doing it in the opposite direction, doing a denary to binary conversion. So let's look at the value 75. How do we convert 75 to binary? Well, we start with the leftmost column, okay? So we're over here, and we compare the value in the column to the value that we're trying to convert. And we say, is 128 smaller than 75? Well, no, it's not, is it? So what we're going to do is we're going to record 0 in this first column on the left-hand side. Now we're going to move one column to the right. Now we're going to compare 64 to our value. So is 64 smaller than 75? Yes. So we're going to record a 1 now in that column. Once we've done that, because we've placed a 1, we need to do a subtraction. So that's 75, which is our original value, minus the 64, where we've just placed the 1, and that gives us a remainder of 11. So we're going to use 11 in the rest of this calculation. Again, we move one column to the right. Now we're looking at 32. Is 11, our remainder, smaller than 32? No. So again, we just record a 0 in that column. Move one column to the right again. Is 11 smaller than 16? No. So again, we record a 0 in that column. We move one column to the right again. Is 11 smaller than 8? Well, yes. So we're going to record a 1 in that column, and again we're going to do a subtraction. 11 minus 8 gives us a remainder of 3. So 3 is what we're going to use in the remainder of this calculation. Move one column to the right. Is 3 smaller than 4? No. So again, we record a 0 in that column. Move one column to the right. Is 3 smaller than 2? Yes. So again, we record a 1 in the column, and then we do the subtraction. So 3 minus 2 gives us a total of 1. Move one column to the right. We're in the final column. We've got 1 left over. The column value is 1, so we're just going to record a 1 in that final column. That means we've used up all of that number they wanted to convert. And now we have an answer of 01001011. We can, of course, double check that this is correct and that we haven't made a silly mistake by reversing the calculation. So we can look at that and go, right, what have I written down here? I've said we've got a 64 and an 8 and a 2 and a 1, so I can add all those together. So 64 plus 8 plus 2 plus 1, does that give us the right number? Yes, it gives us 75. That was the number we were trying to convert. So I've reversed that calculation, and I know now that I have the right answer. Always, always, always double check your answer. It is very easy to make mistakes with this in an exam situation. I see it all the time. So many really good students making simple errors and losing easy marks. Always double check. You should always get these answers 100% right. You also need to be able to perform binary addition. So you need to be able to add two 8-bit numbers together. Now, performing binary addition is actually not too difficult. You just have to remember some simple rules. 0 plus 0 equals 0. 0 plus 1 is 1. 1 plus 0 is 1. 1 plus 1 is 0, carry 1 to the next column. That's because in decimal, 1 plus 1 is 2, and if we convert 2 to binary, we get 1, 0. So that's 0 for this column, and we add the 1 to the next column. And the final rule is 1 plus 1 plus 1 equals 1, carry 1. Because 3 ones equals 3, which when we convert to binary is 1, 1. 1 for that column, 1 for the next column. Note And now this is really important. You cannot just do a binary to denary conversion and then add them up normally and convert it back to binary. You must show evidence of knowing how to perform binary addition. You must show that you understand the rules that are on this slide. Otherwise, you will lose marks. So let's have a look at adding two binary numbers together. We've got 0, 1, 1, 0, 1, 0, 1, 0 plus 0, 1, 1, 0, 1, 0, 0, 1. We start with the least significant bits on the far right, and then we just add them together one at a time. So first of all, we've got 0 plus 1, and 0 plus 1, of course, gives us 1. And now we can move over one column and add up the next. So we move one column to the left. Now we've got 1 plus 0, and that gives us 1. Next column. 0 plus 0, well, 0 plus 0 can only give us 0. Now we get to an interesting one because we're going to have 1 plus 1. And as we've discussed before, 1 plus 1 is 0. Carry 1 to the next column. Again, that's because 1 plus 1 for us in decimal would be 2. 2 in binary is 1, 0. So it's a 0 for this column, and we add 1 to the next column for the next addition. Move one column to the left. Now we have 1 plus 0 plus 0. Obviously, that's just going to give us 1. Move one column to the left. Again, we've got this 1 plus 1, which gives us 0. Carry 1 to the next column. Now, just a note here, sometimes people do the carry on the top. Sometimes they do it underneath. Doesn't matter. Just make sure when you're doing the exam, you show your carries. If you don't show your carries, then they don't know that you understand the rules of binary addition, and you're going to lose marks, okay? Okay, so we move one column to the left again. This time we've got the really interesting case where we've got 1 plus 1 plus 1. So we've got 3 ones together. Now, if you remember this rule, we have 1, carry 1, and that's because 1 plus 1 plus 1 is 3. 3 in binary is 1, 1. So 1 for this column, carry 1 to the next column. So we get to the final column, the most significant bit, and we've got 1 plus 0 plus 0, and that gives us a total of 1, of course. And again, we can double check this. Once we've shown our carries, once we've shown we can do binary addition, we can say, right, 0, 1, 1, 0, 1, 0, 1, 0 converts to 106. 0, 1, 1, 0, 1, 0, 0, 1 converts to 105. 106 plus 105 equals 211. And 211 in binary should be 1, 1, 0, 1, 0, 0, 1, 1. And that is the exact answer that we have. So therefore, we can double check and know 100% that this is the right answer. So if you have time in the exam, you always want to double check this. If you have a look at this example, we now have a problem. We've changed the ones and zeros, and everything's fine until we get to this final column here, you see. So we've reached the end of the 8 bits, the most significant bit, and we've said 1 plus 1. Well, 1 plus 1 gives us 0, that's correct. But now we should carry 1 to the next column. But there is no next column. We're dealing with an 8-bit number. We can't just magically create a 9th bit. In our simple system that we use for the exam, we're limited to 8 bits only. So what does this do? Well, the carry is lost. We have what we call an overflow error. And this is where you're trying to continue into a new column, into a value greater than you can store. So if you get a situation like this in the exam, sometimes you will, you don't just create a 9th column. You don't say, oh, well, I'll create a new column here and put a 1, and now my answer is 1, 0, 0, 0, 1, 0, 0, 0, 0. No, don't worry about that. Just write the answer in as 0, 0, 0, 1, 0, 0, 0, 0, and then just put overflow error underneath, just to show that you've got that understanding. You can't just make up a 9th column. You're limited to 8. You have an overflow error. And almost certainly if you get an addition like this in the exam, the next question will be something like, explain what's gone wrong with the previous addition. Finally, we're going to take a look at binary shifts. Moving the digits in a binary number left or right is called a binary shift. For example, each time the value is shifted one place to the left,
the number is multiplied by 2. Why is that? Well, let's take a look. Let's take the number 33 in binary, which is 001000001. What we're going to do is shift everything one place to the left. So if I start with the first value here, I'm just going to shift that 1 to the left. Take the next number, shift that 1 to the left, shift the next one, and the next one, and the next one, and the next one, and the next one. The final value here is a 0, so there's nowhere really to shift that to, but zeros don't hold any value when they're leading 0, so we can not worry about that just now. And that just means we have to fill in an extra 0 here just to make up the full 8 bits. Now that we've finished doing the left shift, we have a final number here of 01000010. If we compare these two numbers, we can see that after the shift we've jumped from 33 to 66. So our original value here was 33. So yeah, 001000001. We've shifted everything 1 to the left, and now we should get 66. So we've got a 64 here, yeah, and we've got a 2, yep. So 01000010 is 66. Binary shifting one column to the left always multiplies the original value by 2. If we left shift again, we find that we get 132. So again, we move everything one column to the left, and that gives us 100000100. Again, we're just going to add in that extra 0 there for the placeholder after we've left shifted. So now we've multiplied the original value by 4. We've gone from that original value to 132. So 33, 66, and now we're at 132. But if we try to left shift one more time, the most significant bit will be lost. This results in the number 8 being stored, and this is an overflow error. So we've got another overflow error. So again, just to explain that, if we were to left shift everything here and move every column along 1, well, mostly that's fine. We can shift that, we can shift that, we can shift that, we can shift that. All the zeros are nice and easy to shift. But then we've got a problem. I've run out of digits now. When I try and shift that final 1, there's nowhere to put it. It's lost. I'm not multiplying 132 by 2 to get 264. I'm going to end up with just the number 8 being stored because I have this overflow error. Let's look at doing it in the opposite direction. Each time the value is shifted one place to the right, the number is divided by 2 rather than multiplied by 2. So let's take a look at a simple example. We're going to look at the number 68, which in binary is 1000100. So again, we're going to shift this one place to the right and add 0 to the left-hand column, which is going to give us 34. So again, let's do that. So again, we start at the most significant bit, and we're just going to shift everyone 1 to the right this time. 1 to the right, 1 to the right, 1 to the right, 1 to the right, 1 to the right. And then we're just going to add that 0 as a placeholder there just to make the full 8 bits. And notice we do actually lose this 0 here. But that's okay, it's just a 0. Losing that's not a problem. So if we right shift again, we find that we get the value 17. So again, we're right shifting twice now. Everything's moved 2 columns down, and now we have the value 17. So we've actually divided that original value by 4. So right shifting once divided by 2, right shifting twice divides by 4. Right shifting 3 times would, of course, then divide it by 8. However, in this particular case, if we try to right shift one more time, the least significant bit will be lost. I've got the most least significant bit here. Obviously, that's a typo. The least significant bit, the LSB, will be lost, and this will cause a loss of precision. So again, why is that? Well, let's shift everything over. That gets shifted over. That gets shifted over. That gets shifted over. And we continue, so on and so forth. But again, we've got a problem now. we've got a 1 left over, so 1 has value, and we try and shift that, there's nowhere to put it. We have a loss of precision. So if you get an example like this in an exam, you can explain you're losing the least significant bit, and this will cause a loss of precision. Note that loss of precision and overflow errors only occur when the most significant bit or the least significant bit is a 1. Losing zeros is fine. You don't want to lose any of the 1s because that will cause an error. Okay, that was quite a long presentation to do. I'm going to stop it there. We'll look at hexadecimal in the next class. So just remember, you need to be able to do the following. Convert from binary to denary, convert from denary to binary, add two 8-bit numbers together, watching out for those overflows. You need to be able to conduct binary shifts. Binary shift to the left will multiply by 2. Again, watch out for overflow errors. If you binary shift to the right, it divides by 2 for each column you move along, but watch out for precision errors. Thank you for watching the video. Good luck with all your studies.